Welcome to the Fuel Pulse Show podcast, where we talk about all things fuel for all kinds of people. I'm your host, Eric Bjornstad, and I'll be your guide through the ever-changing world of fuel. Here at the Fuel Pulse Show podcast, we focus on issues and problems and solutions that people encounter when they use and manage all the common kinds of fuel that they use at work and at home. And we like to talk about the things that use that fuel as well. The big engines and the equipment that use that fuel on the job, right? As well as the vehicles and generators and small engines that people tend to have at home. And that means the Fuel Pulse Show podcast is for everyone. So, what are we going to talk about on today's episode? Well, one of the topics that we like to talk about on this podcast is what the different diesel fuel properties and tests mean from a practical standpoint, especially the ones listed in the D975 diesel fuel specification from the ASTM. Now, the D975 tests are important because together they represent the critical benchmarks for quality and performance within the diesel fuel industry. Because you really need something that ensures that fuels meet specific criteria for safety and efficiency and even environmental impact. And D975 is what defines the slate of properties that the industry has agreed best meets those marks. So within ASTM D975, there's a test called the distillation test, also noted as ASTM D86. And this is one of the more important tests for ensuring that diesel fuel has the proper combustion properties. And that's what we want to talk about today, this fuel distillation test, why it matters, how it can help you tell if your fuel has gone bad. We might even talk on some common explanations about why the fuel happened to have a bad test result and what you might be able to do about it. So let's get this party started. And to do that, we want to set the table for understanding why the distillation test is important. So understanding fuel distillation properties is important for professionals managing or using fuel in their operations for a few key reasons. A fuel's distillation properties offer insight into the fuel's composition, its quality, and its performance characteristics. And the distillation properties directly impact, if they're off, they directly impact engine efficiency, operational costs, even the engine's maintenance requirements. They can affect those too. So here's why distillation properties matter for these kind of considerations. First, how does it affect fuel performance and efficiency in the engine? And the answer to that is two reasons: volatility and the fuel's temperature adaptability. Okay, so let's talk about each of these. First, volatility. Distillation properties reflect the volatility of the fuel, which reflects how easily the fuel vaporizes. And proper vaporization is really essential for efficient combustion in diesel engines. If the fuel is too volatile, then it's going to vaporize too quickly, leading to things like premature ignition and engine knocking. Conversely, the fuel that's not volatile enough is not going to vaporize adequately, and you're going to get incomplete combustion, reduced efficiency, and higher emissions. Now, later, we're going to talk a little bit more about these and run down exactly how different distillation results indicate good or bad volatility. So that's number one. Number two is that thing we call temperature adaptability. So the distillation curve, and we're going to explain what that is a little later, the distillation curve helps determine the fuel's performance across different temperature ranges, from cold startups to high temperature engine operation. Having these properties where they should be ensures that that particular fuel is suitable for the specific environmental conditions and operational demands that it's going to face. And therefore, it ensures optimal engine performance and reliability in all of those situations. So next, distillation properties matter for clean combustion and reduced maintenance needs. So clean combustion, if you have properly distilled fuel that has the right distillation properties, it's going to burn more completely. It's going to make fewer deposits on engine components like the injectors and the pistons and the cylinders. And this then is going to minimize wear and tear and extend the engine life, maintain efficiency. Pretty much a complete slate of good things, right? And then reduce maintenance needs. Using fuel with the appropriate distillation characteristics leads to fewer engine deposits and less stress on critical components, which means you end up reducing the frequency and cost of engine maintenance. Now, what about regulatory compliance? Fuel distillation properties affect the emissions, and using fuel that has good distillation properties helps ensure compliance with those environmental regulations, which leads to, avoiding fines, maintaining a good operational reputation, and if it's really important to you, contributing to environmental sustainability. So distillation can relate to regulatory compliance in those ways. And then there's the thing people kind of take for granted, the safety consideration, right? I mean, one of the things that we'll end up mentioning as we break down the test is we'll talk about a measurement called the initial boiling point of the fuel, or the IBP. Now, the distillation test tells you what it is, and it can inform on safety risks like flammability and handling precautions. And then last but not least, distillation test plays a part in quality assurance. See, regular testing of the fuel distillation properties as part of a quality assurance program can help identify or point out or flag when you have substandard or contaminated fuel. And it'll do this before it starts causing problems, which means you can be proactive in your management and you can mitigate potential operational risks before they become really costly. So, for all of these things we just mentioned, the fuel's distillation properties actually matter for in all those respects. So, what we want to do in the rest of this episode is unpack a little more about this D86 distillation test, how they do it, how they interpret the results, and then if the results come back, shall we say, subpar, what might be the reasons for that failure? And is it even possible to fix a distillation problem? Maybe we'll take a crack at that question too. So, we're going to try and cover all that in the rest of our time together. So let's start by making sure we have a clear understanding of how this D86 distillation test actually works, or how it's actually conducted. So its official name is ASTM D86, distillation of petroleum products and liquid fuels at atmospheric pressure. And it's a method used to determine the boiling range characteristics of various petroleum products and liquid fuels. To run this test, you take a 100 milliliter sample and you heat it up until it starts boiling. And then you keep heating it until all of it evaporates. Now, what the test is looking for is what percentage of that sample has vaporized at different temperatures. At what temperature has 10% of that sample vaporized? What temperature has 50% of it vaporized? What temperature has all of it vaporized? Now, usually they're not going to track, every single percentage, like trying to find what percentage is 18% vaporized. They don't do that. But they do track every 10% increment. Start with initial boiling point, which is 0, 10%, 20%, 30%, 50%, all the way up to 100%. And then they take this information, this temperature information, and they plot it. And they create what's called a distillation curve. And the distillation curve tells us something useful about the fuel's volatility and the fuel's combustion characteristics. Now, like we said, they don't look at every single temperature percentage, right? 18, 19, 20, 21%, whatever. They don't do all of those. And typically they don't even though they plot data for all of the 10% measurements, they don't necessarily look all the time at all 12 or however many there are if you include the starting and the end point. What the test is actually concerned with most are 5 measurements, and they are the initial boiling point. Remember that 0 point. Initial boiling point, IBP, 10% point, 50% point, the midpoint, 90% point, and then the final boiling point. 100% of the sample has vaporized. And each of these measurements can give us insights about the fuel. So let's talk about each of these. And what we want to do is we want to talk about their significance, and we want to talk about what you might expect to see if each of these or any of these is too high or too low, right? Okay, so start with initial boiling point. So that's the point at which the fuel first starts vaporizing, first starts boiling. Now, if you have fuel that has a lower initial boiling point, conceptually what that means, if it boils at a lower temperature, that means it vaporizes more readily, more easily, right? That makes sense. And one advantage of having fuel, or one situation where having fuel that vaporizes easily is an advantage, is in cold weather, where this is going to come up multiple times through the discussion of the other points. Fuel that vaporizes more easily is more volatile. That fuel helps the engine start more easily in cold weather. So it aids cold starting. Now, interestingly, when they're at the refinery and the refinery is formulating these fuels, the refinery can choose to alter the way it blends diesel fuel, and they will actually try to move that initial boiling point up or down, depending on what's needed most in the climate that fuel is going to be used in. So if it's going to be used in colder climates, what they will do is they will, since colder climates require a lower initial boiling point, the refinery will actually blend more of the lighter fractions into the fuel so that the fuel is more volatile and it starts easier in the cold climate. Conversely, in a hotter climates don't need more volatility. In fact, if it's too volatile, as we're going to find out, that can be a problem. What hotter climates prefer is maybe having more power. And so what the refinery may decide to do is they may decide, instead of blending more lighter fractions, they'll actually skew it a little bit on the heavier side and blend more heavier fractions in there to increase the power and maybe help tamp the volatility down a little bit for the hotter climate. So the refinery can actually do things before the fuel even goes out into the marketplace to try and make the fuel more suitable for the kind of climate that or environment that it's going to be used in. So that's initial boiling point. The next thing they look at is the 10% point. 10% point is the temperature at which 10% of that sample, of the volume of that sample, has vaporized. So the question that we're going to ask, and we're going to ask the same question of the 50% and the 90% and the final boiling point, same questions. What happens if that 10% point is too high or too low? And really what we're saying is if it's significantly too high or significantly too low versus where we normally should expect it to be. So let's start with too high, right? Now, from a composition standpoint, if the 10% distillation mark of that fuel is too high, what that tells you about that fuel's composition is that fuel has more of those lighter, more volatile components in its makeup. It indicates that that fuel's lighter, more volatile components are actually requiring a higher temperature than normal for them to vaporize, which means the fuel does not vaporize as easily as it should at lower temperatures. Now, if you were paying attention, you may notice that I actually made a little bit of a mistake there. I started to say the opposite of what I wanted to say. And Some of that comes from the fact that when we talk about, as we talk about volatility versus distillation, they actually work in opposite manners. So when we say a fuel's distillation mark is too high, what that actually means is that its volatility is lower. So it's the opposite, right? And then vice versa. If the distillation point is lower than it should be, that means it's actually more volatile. So you just have to keep that in mind so you don't get it confused. So let's repeat ours. Let's backtrack a little bit and repeat this so that we fully understand this. If the 10% distillation point is too high, that means it vaporized, the 10% of it vaporized at a higher temperature later, if you will, than it normally would. And what that indicates is that the parts of the fuel that are lighter and more volatile, those are actually not vaporizing soon enough, if you will. They're requiring a higher temperature than normal to vaporize. So the fuel's volatility is not as high as it should be. And so what that's going to do, remember we said a more volatile fuel means easier cold starting in colder temperatures. Well, in this case, if the 10% mark is higher than it should be, that means it is not volatile enough. And that means it's going to have problems. That engine's going to have problems starting in cold weather because in cold conditions, that engine needs proper vaporization of the fuel for efficient ignition, right? And because that fuel is not volatile enough in those cold temperatures, you're going to get poor starting and poor combustion quality when the engine's cold. And you're also going to get all those things you would associate with poor combustion quality and poor operation. You're going to get rough idling. You're going to get reduced power. You're going to get increased fuel consumption. And all that's going to happen until the engine reaches its optimal operating temperature. So that's the problem if the 10% distillation point is too high. But what happens if it's too low, right? Remember, we said too low means more volatile, or lower means more volatile. So if the 10% distillation point is significantly too low, that means that the fuel probably contains a higher proportion of those lighter, more volatile components that tend to vaporize at lower temperatures. And that ends up dragging that 10% temperature down, makes it too low. So if you have a 10% distillation point that's too low, you get several potential issues. First, like we said, a low 10% point means the fuel's vaporizing sooner, which means it's more volatile, which can lead to, if you're in warm weather, it's going to lead to higher evaporation, what they call increased evaporation losses in warm weather and at high temperatures. And that's not a good thing. It's not good to have something like that because more evaporation losses means you're going to waste more fuel. And you also have a little bit, it's going to affect the fuel system's pressure and increase the risk that you're going to run into vapor lock issues, which you don't really want. So that's what happens if your 10% distillation point is too low there. Okay. There's also pre-ignition risk. Fuels that have that higher proportion of volatile components that result in it vaporizing sooner at 10%, those are more likely to ignite prematurely in the combustion chamber, which gives you that engine knocking that you don't want. And there's also a potential impact on engine lubrication. I mean, if you have more of those highly volatile components in the diesel fuel, they are more easy, they will more readily condense into crankcase oil. That results in dilution of the oil, reduces its lubricating properties, and leads to increased wear in the engine components, meaning over time, practically speaking, you might find that you need to change your engine oil more frequently under those kind of situations. And then finally, there's also consideration of emissions and environmental impact. So while a 10% distillation point can make cold starting easier, or it can improve cold start emissions by ensuring more complete combustion at lower temperatures, it can under this at the same time lead to higher what they call VOC, volatile organic compounds, higher VOC emissions. And VOC emissions are bad because they are a key contributor to smog formation. So, to summarize, for that 10% temperature, if it's too high, the fuel's not vaporizing as well as it should, means it's going to be harder to start in cold weather, and it's going to run rougher and less efficiently while it's cold until the engine warms up. If it's too low, it's going to vaporize too easily, which means you have a greater risk for vapor lock. You have higher evaporative emissions that are bad for the environment. You can have more engine oil dilution, and there's even evidence that it contributes to smog emissions, even in cold weather. So that's the 10%. What about the 50% midpoint? That's the next important one that they care about, the 50% measurement. That indicates the temperature at which half of the fuel sample, 50% of that, has vaporized. And ideally, you want this 50% point to be a nice balanced midpoint, because a balanced midpoint at 50% ensures good fuel atomization and optimal combustion efficiency. But if it's too low, you have increased fuel volatility, because a lower 50% distillation point indicates now, because we're not just talking about 10%, we're talking about 50% of the fuel being gone. So if that 50% point's too low, then you're not just talking about the lighter fractions reflected in 10% measurement. You're talking about what a greater, more significant portion of the fuel is doing. You're saying that 50% of the fuel is more volatile, which means it's vaporizing at lower than normal temperatures. Just the same as with a low 10% point, you might get a little better cold weather performance, but you're going to have a trade-off. You're going to have a trade-off with increased evaporative losses, higher smog forming emissions, and even also this one starts coming to play more with 50% than with 10%. You may start to see potential issues with fuel storage, because what if it's too low, then you're going to start seeing more of the lighter fractions of the fuel actually evaporating in storage and disappearing more readily, and that's not good for the fuel in storage. Now, if the 50% measurement's too high, number one, hard starting, poor cold weather performance. A higher 50% distillation point means, just as with the 10% measurement, the fuel does not vaporize as easily at lower temperatures, which causes hard starting issues, poor engine performance in cold weather, because the fuel's not atomizing and combusting efficiently when it's cold. And then also incomplete combustion. Fuel that vaporizes higher at a high, or I should say, fuel that requires a higher temperature than normal to fully vaporize is not going to burn as completely in the engine. So you're going to get higher emissions, particulate, carbon monoxide, unburned hydrocarbons, VOCs. You're going to see that. You're also going to get greater formation of deposits in the fuel injectors and on the combustion chamber surfaces. And, as you would expect, decreased fuel efficiency, because the engine is going to require more fuel to produce the same amount of power. So that's the 50% mark. Now, the fourth and the fifth measurements that they look at are the 90% and the final boiling point. And while the previous ones, the initial boiling point and the 10% and the 50%, while those appear to most affect vaporization and cold weather performance, these final two, the 90% and the final boiling point, these have more of an influence on the power and the emissions of the engine. So the 90% point represents the temperature at which 90% of that sample has vaporized. So while the 10% point down here tells us something about what the lighter fractions of that fuel are doing, the 90% point, conversely, all the way over here at the other end, the 90% point tells us more about what the heavier fractions of the fuel are doing and how those are impacting the engine's performance. So if that 90% measurement is too low. This suggests that the fuel is more volatile overall because a large portion of it is vaporizing at lower than normal temperatures, vaporizing sooner. So it's more volatile. Now, as with previous points, if you have greater volatility, you're going to get better cold weather operability. However, in warmer conditions, you got that vapor lock problem again, and you're going to have increased fuel consumption in warmer conditions. But there's also, it can have an impact on lubricity and fuel stability. If you have too low of a 90% point, then what that tends to mean is that that fuel doesn't contain as many of the heavier components, which means it actually contains more of the lighter components. And if it contains more of the lighter components, you get two problems. First of all, it doesn't lubricate as well, so the lubricity is lower. But then the second thing is that the stability is lower as well, and you have a greater risk of those lighter, more volatile fractions evaporating off over time. So, too low of a 90% point affects the lubricity and the stability. That can potentially affect the fuel pump. It can affect the injectors, and it increases the risk of fuel degradation during storage. So that's the slate of things that happens when the 90% point is too low. Now, if the 90% measurement's too high, what do you get? Well, first of all, a higher 90% point indicates that the fuel contains more heavy components that vaporize at higher temperatures. This can lead to difficulty in starting the engine in cold conditions because, again, fuel doesn't atomize and ignite as readily under cold conditions if it's not as volatile. And also, these heavier components that don't fully vaporize and don't fully combust, well, when that kind of thing happens, that means you get deposits that are formed on your fuel injectors and in the combustion chamber and on your piston rings. And those deposits have an effect. They can decrease the engine efficiency. They can increase the emissions of the engine. They can necessitate more frequent maintenance. Plus, you're going to have that thing that everybody hates, reduced fuel efficiency. And then the last point of the five that they typically consider, the final boiling point. Final boiling point is the temperature at which complete evaporation of the sample has occurred. If the final boiling point is too low, that means that the fuel does not have enough of the heavy components in it. It means the fuel will be too volatile because if it doesn't have enough of those heavy components, that means that it has too many of the lighter components. And the lighter components are, of course, the ones that are more volatile. So the fuel is going to be too volatile. It's not going to have as high of an energy value. And that's going to mean your mileage is going to be lower. Now, on the flip side, if you have a final boiling point that is too high, you're going to get more situations where you have incomplete combustion, you have more deposits formed in the engine, and you're going to have higher emissions. So, 5 points that they typically look at. Initial boiling point, 10%, 50%, 90%, and final boiling point. As we said, they take these data points, they plot them on, they create a distillation curve. Now, for diesel fuel, a well-balanced distillation profile, or what they might call a gradual slope on a distillation curve, with the various temperature points all falling where they should be. When this is true of the fuel, then the fuel is going to give you easier startup, smooth warm up. It's going to give you the most efficient combustion, the most power delivery. It's going to minimize emissions, minimize formation of harmful deposits. You're going to get the optimal engine performance and lifespan that you want if the fuel is in spec with a proper distillation curve. If that's not true of the fuel, if it's offline on any of those particular points, whether too low or too high, then it's going to give you the kinds of problems that we've been talking about. So now that we've got an idea of the kinds of problems that we could see if our fuel's distillation properties aren't where they should be, makes sense now to ask the question, how could that have happened? What are the most likely reasons for test failure, so to speak? Well, we have to start by saying that it's almost never going to be the fault of the refinery because all diesel fuel that leaves the refinery has been heavily tested for quality assurance to make sure that when it goes out into the marketplace, it has the right combustion characteristics. And yet, if anything happened on the way to the forum, so to speak, our fuel's distillation properties aren't where they should be. And we're trying to figure out why that happened. So let's consider the most likely reasons for that change are number one, possible contamination with something, or number two, possible degradation of that fuel due to improper storage. Okay, so let's unpack that first reason, contamination with something else, whether it's other fuels or other substances. Most likely or most commonly, if we were talking about contamination, we would probably be talking about contamination with either gasoline in diesel fuel or something else like some other kind of volatile compound. So that's number one. Or we could even be talking about water contamination. So let's take the first. If you get a gasoline contamination or contamination with some other more volatile hydrocarbon, like, I don't know, naphtha or something, I don't know. If your diesel is contaminated with gasoline or a more volatile fuel, what that's going to do to your distillation curve is it's going to lower the initial boiling point and that first part of the curve, the 10%. So it's going to alter the first part of the distillation curve if it's contaminated with more volatile substances. Now, water contamination actually works on the other end. Water contamination will affect distillation results because water has a higher boiling point than most of the diesel components out there. And so, because of that, if you have water contamination in that mixture, it's actually going to increase the observed endpoint temperature. It's going to raise the boiling point of the final boiling point. So, water contamination alters the last part of the distillation curve. So, whether it's contamination with other volatile substances or contamination with excess water, both of these can throw your distillation curve off at different ends. Now, second most likely explanation could be a result of degradation of the fuel from being in storage. Now, how does that work? Well, first we have to consider the oxidation processes. Fuel gets exposed to oxygen, and over time, exposure to oxygen leads to formation of heavier compounds like gums and varnishes and other kinds of oxidation products. Now, the thing about these heavier compounds that form over time is that they have higher boiling points than before. And so you get enough of those in there, enough of those formed in there over time, that actually will shift the fuel's distillation curve towards higher temperatures. So if your diesel distillation curve comes back high, but not just at one specific point, but maybe at multiple points on there. So it comes back high in multiple places. That could be an indication that the fuel has degraded in this way. And then also consider the effect of excessive temperature fluctuations. If your fuel stored in, let's say, an above ground tank, which are more sensitive to ambient temperature changes, if you have frequent or even extreme temperature changes during storage, that can cause or accelerate evaporation within the storage tank, evaporation of the lighter fuel compounds. And that will, if those lighter fuel compounds evaporate and go away, the fuel's average boiling point is going to rise and it's going to push the curve upward. Sometimes we don't think about those kind of events when we think about stored fuel, or we don't think about the longer our fuel is stored, the greater chance that some parts of it are going to evaporate and disappear. But that is a reality. It does happen. And when it does, you can get tangible effects like this. And then last thing, microbial growth can also skew your distillation results because the microbes produce byproducts. The microbial byproducts can change the chemical composition of the fuel and affect its distillation curve because the microbes tend to introduce heavier, less volatile compounds into the fuel. And those can have an effect of changing the distillation curve. Okay? So if you have any of these things going on in your fuel, any of these can actually change the distillation of your curve in certain characteristic ways, whether it's contamination, degradation due to improper storage, or presence of various unwanted substances. Any of these can significantly alter the distillation properties of the diesel fuel and lead to failure or being out of spec in the ASTM distillation test. And when that happens, it can lead to all those kinds of problems that we talked about earlier. So at this point now, okay, we know now all about what might cause these problems. However, one thing we have not talked about is what you might be able to do about them. Because we know somewhere there's a fuels manager or an operation manager who is saying, yeah, it's probably because of X, Y, or Z in my fuel, but just tell me what my options are on what to do about this problem. Well, let's talk about that. So, for fixing an out of spec distillation reading, the main options that you have, once you've mitigated issues with microbial contaminated excess water, right? Once you clean those things up, that's the first thing you're going to need to do in any kind of situation is make sure you've gotten rid of excess water, make sure you've killed off any microbial growth. Now, once you've cleaned all that up, the main solution lines for correcting off spec distillation problems really comes down to blending the fuel with either higher or lower volatility compounds. In other words, things that either have higher or lower boiling points. Blending some of those into your fuel to try and get that distillation, up or down to where it needs to be. And before we run through some of those candidates, however, we do need to take a little bit of a step back and just kind of throw out there, say, we do realize we need to be realistic here. When somebody's there says, well, your solution is just blend some different things into the fuel. Sounds like, when they say that, it sounds like they're talking to a refinery, right? But an operations manager or a fleet manager, how likely is it that they're going to have access to the kinds of things that could be blended in to fix an off-spec distillation problem? Well, part of the answer to that question lies in what it is that you're proposing to put in there. So let's say that your distillation curve is too high. So you need to lower the distillation properties. Now, remember earlier we said they worked in opposite directions. If you need to lower your distillation properties, what you're actually saying is you're trying to increase the volatility of the fuel. So what would you do? Well, you would look to blend in another kind of fuel or hydrocarbon that's more volatile than diesel is, which means either naphtha or more commonly gasoline, right? But, take that word but, underline it multiple times. But you do have to be really careful about doing this because not only is it really easy to overshoot, but if you're blending gasoline in there to change the distillation properties, you might be able to solve the distillation properties, but at the same time, you would be running the risk of making some of the other properties of the fuel drop out of specification at the same time that you're fixing this particular one. And ultimately, that doesn't do you any good because you're basically creating a problem and solving another one. But the simple solution, the basic solution is for a distillation curve that's too high, blend in a more volatile substance like gasoline to lower it down. Now let's take the opposite. What happens if your distillation curve is too low? In other words, it's too volatile and you need to decrease the volatility. Well, the popular candidates to blend in there are either number one diesel fuel oil, kerosene, or gas oil. Both of these have a lower volatility than your typical number two diesel. So you could use them to adjust the distillation reading that's too low, kind of to raise it up. Because again, remember, lower volatility is reflected in a higher distillation reading. Now, for most parties who are running into a problem with the distillation curve that is out of whack, so to speak, they may just elect to get rid of the fuel if the difference in distillation properties is serious enough that they don't feel that they can actually use the fuel. Now, if you do feel adventurous enough to try correcting this problem by adding some of these things, you do need to go in. You need to go into that with your eyes wide open and be prepared to do some testing at the end to make sure that none of the other properties have fallen out of range or you were trying to fix this other problem. So, while you can't fix every possible instance of contamination, one thing that should be clear through the course of this episode is remember, we said that water contamination can throw your distillation off, and also the fuel storage issues happening. Both of those can actually change a distillation curve. So one of the things that we can kind of take away with this is that keeping water and getting rid of water in the fuel and using fuel stabilizer, both of those can actually give you secondary benefits of helping to protect your fuel's distillation properties. Because it's pretty clear that those kind of best practices have that added benefit of helping to protect the fuel's distillation properties as well. So, as we wrap up today's discussion on fuel distillation and its significance, remember that ASTM D86 is not just a technical procedure, it also happens to be a vital tool for ensuring that our diesel fuel performs optimally in our engines. Remember that the test key's on those 5 data points, right? And that being too high or too low on particular ones can lead to particular problems. Initial boiling point can lead to hard starting, poor cold weather performance, to fuel not being volatile or being less volatile, and struggling to vaporize in cold temperatures. If it's too high. If your initial boiling point is too low, then that suggests the fuel is too volatile, which means you could have excessive evaporation. You could run the risk of pre-ignition, potentially leading to engine knocking. If your 10% and your 50% points are too high, that means the fuel is vaporizing at too high of a temperature, meaning it's not volatile enough, meaning you're going to risk incomplete combustion, reduced fuel efficiency, and higher emissions, especially in cold weather. If your 10% and your 50% points are too low, that means it's too volatile. Higher likelihood of vapor lock, higher evaporative losses, and potential negative impacts to the engine lubrication and emissions. And then your 90% point and your final boiling point. If they're too high, that shows that the fuel contains too many of those heavy components that only vaporize at higher temperatures. That means you're going to have difficulty starting, reduced performance in cold weather, and more engine deposits and less efficiency in the engine. And then if the 9% point and the final boiling point are too low, that suggests that the fuel doesn't have enough heavy components in it, meaning it's overly volatile, so to speak, has reduced energy content, you're going to have lower emissions. So understanding all those outcomes and their relationship to the fuel properties, that can help us better grasp the importance of the fuel's quality and the role of distillation tests in telling us about that fuel quality. Ensuring that our diesel fuel meets the right distillation properties. If you can do that, you're not only going to protect your engine, you're going to optimize your performance, and you're going to minimize your environmental impact too. And so, there you have it, a brief overview of why the fuel distillation test matters and how it affects everyone who uses diesel fuel, from everyday drivers to professionals who are managing fleets and engines. So that is going to do it for today's episode of the Fuel Pulse Show podcast. Again, thank you very much for joining us. We're going to have links to everything we talked about in the show notes. So we appreciate you letting us offer you some insights about fuel distillation properties, the good, the bad, and the ugly, so to speak. So if you have not done so already, feel free to subscribe to the podcast on your platform of choice, whether that's iTunes, Stitcher, Google Podcasts, Amazon Podcasts, Spotify, any of those. And also, if you feel so inclined, we'd really appreciate if you left us a rating, because good ratings really do help us with the algorithms and really do help us get the word out to people who are trying to find us. So anyway, that's it for today. And thank you for joining us. And we will see you next time on the next episode of the Fuel Pulse Show podcast.